Hi, I'm Professor Melko, Chemistry PhD, and your university chemistry professor. Today we're going to learn about naming and writing formula for ionic compounds, molecular compounds, and acids. Once we do that, you know what's next.
Are you pondering what I'm pondering?
That's right, taking over the world. Let's jump into the lecture. Okay, so today we're going to start with writing chemical formulas for ionic compounds. Right? And we learned in the last lecture, feel free to go back and watch that video, what is an ionic compound? It's when we combine a metal with a nonmetal. Okay? And usually we represent these compounds with something called a formula unit, or just this simple representation of what the compound looks like in symbolic form using the elemental symbols like sodium, chlorine. Okay? So these are neutral molecules that's important to keep in mind as we move forward, that overall sodium combining with chlorine is neutral, even though there might be an exchange of electrons involved. And that's what happens with a chemical bond. Okay, so the positive charge on sodium likes to be +1, exactly cancels the negative charge on chlorine, -1. All right, so we also have something like potassium nitrate. This is a ternary ionic compound, which is a polyatomic NO3 -1, being balanced by a potassium +1. Okay, so these are what chemical formulas look like for ionic compounds. How do we come up with them? Right? We come up with them using something called the crossover rule. Right? Keeping in mind that the charges must balance and overall this aluminum oxide must be neutral. Right? How do we come up with these numbers 2 and 3? Okay? The way I like to teach this is consider what the charge is on each ion. Okay? So aluminum, you can look in the periodic table. We can go back a slide. It is right here. It needs to lose 1, 2, 3 electrons to achieve a noble gas configuration. Losing 3 electrons means it's a 3 positive charge. Similarly, for oxygen, it needs to gain 2 electrons to become a noble gas configuration, so it's 2 minus. So the numbers I come up with are basically crossing over the charges to the other element. This will ensure then that the charges are balanced. Okay, so that's how we get aluminum 2, oxygen 3 for our formula for aluminum oxide. Now, it's important to know that you only use this crossover rule, right, if these charges are not equal. Okay, so if instead it was something like barium, which is +2, with oxygen 2 minus, we don't cross those over to make barium 2, oxygen 2. That would be wrong. Okay? Since it's already a 1-to-1 ratio, I don't need to cross them over. I just keep each element in that 1-to-1 state. So it's just Ba1O1 for barium oxide. Okay, so using the crossover rule now, let's try to put this in practice on something like aluminum chloride. We just expressed that aluminum is 3+. Chlorine we can find on the periodic table here. It needs to gain 1 electron, and electrons are negative. So chlorine is -1. We can cross these over now to get aluminum 1. And we don't write 1s. It's implied if we write nothing. So we just leave it as aluminum without the 1. And chlorine is then going to have a 3. So the formula here for aluminum and chlorine when they combine to make aluminum chloride is AlCl3. Okay, so you really want to master that crossover rule and be able to do it efficiently, because as we move on with chemistry, we're going to have to come up with these formula and then write reactions and then balance reactions. Writing chemical formulas for ionic compounds can be a little bit more complicated once we involve polyatomics. Okay, remember here's an example table of the polyatomic ions. We covered this last video, so feel free to go back and watch that if you're not familiar with these ions. You're going to do it the same way, though, when you're combining the positive ion with this polyatomic anion. Here, the charges are equal, 2+ and 2-, so I don't have to cross them over, and I just write MgSO4. However, where a lot of students get confused is when they're not equal, and I have something like magnesium 2+ combining with hydroxide, OH1-. Now I cross these over. The 1 from hydroxide becomes a 1 on magnesium. Again, I don't write a 1. The 2+ on magnesium goes outside the hydroxide. Okay, but if you write it like this, the 2 is just on the hydrogen. I need it to be on the whole unit here of hydroxide, so you must use parentheses here around the hydroxide unit. That means this 2 is getting distributed and there's 2 atoms of hydrogen and 2 atoms of oxygen. Okay, so make sure on these polyatomics you use parentheses if there's a subscript, right? There is no set of parentheses on sulfate because there's just one of them, so I don't need those parentheses. Let's put this into practice. What is the formula unit for the compound when magnesium 2 plus combines with NO3 minus, which is nitrate? Again, the crossover rule suggests magnesium gets this 1, and nitrate gets a 2. But I realize now that nitrate is a polyatomic, so I'm going to put it in parentheses before I write this subscript 2. And so here is the formula for magnesium nitrate. Now, something else you might be asked to do is assign the charges from a chemical formula. Remember that these chemical formulas are always balancing the positives with the negatives so that they're neutral overall. Okay, so in this compound, which is chromium Cr, combining with nitrogen, I know overall this is neutral. Okay, and I'm going to use that to figure out the charge on chromium. Okay, so I might be asked to identify what is the charge on chromium in this compound. Because if I go to name it, we'll see that I need to know what the Roman numeral is for the charge on chromium. Okay, that's what we're moving towards. So let's put this into action, and let's consider overall I know chromium 3N2 is neutral, right? I know then whatever the positive charges are from chromium, balance the negative charges from nitrogen. Do I know what the charge of chromium is? No, but I can figure it out. Do I know what the nitrogen charge is? Yes. Nitrogen is here. It is always 1, 2, 3 electrons away, so it is 3 minus. So I'm going to create this little sort of matrix here to keep track of these charges. Each nitrogen atom is 3 minus, but there are 2 nitrogens. So I multiply going down here, and overall the nitrogens are contributing 6 minus charges, 6 negatives, 6 electrons in excess. Okay, I know this 6 minus must be balanced by the chromium. Why? Because 6 plus and 6 minus must sum to 0, right? This is neutral overall. And so by identifying the charge on nitrogen and the total charge on nitrogen, I then know the total charge on chromium has to be the same. And so going up now, I divide 6 plus divided by 3 is 2 plus. And so the charge here on chromium is 2 plus. So multiply going down, divide going up to identify the charge on chromium. So if I had to name the chromium ion involved here, it's the chromium 2 ion. So remember, we described this charge on a transition metal with the Roman numerals, as described in the previous lecture. Okay, so now we're going to combine all of this and name these ionic compounds. Remember, last time we learned how to name cations. For ions, it's usually just the element in the name, like magnesium ion. For anions, we add a IDE suffix or use the polyatomic entry from the polyatomic table. So NO3 minus is nitrate. Br minus, bromine becomes bromide. Okay, so that's anions adding this IDE suffix if it's a monatomic anion, one type of element like this, one atom. So let's look at this for Mg and O. Mg magnesium is just called the magnesium ion. O, oxygen becomes oxide. So overall, this is magnesium oxide. So for ionic compounds, we're just smushing together the name of the cation with the anion and dropping the words ion. Right, so this goes away and this goes away to give us magnesium oxide. If the metal is a transition metal, which means it probably has different types of charge states, then I have to figure out what the charge state is on that transition metal before combining it with the anion. And so for the same reason here, HGS, which I identify as the mercury 2 ion, combines with the sulfide ion. I drop the words ion to make mercury 2 sulfide. Okay, this means in our previous example here, what is the name for this compound? Okay, it's chromium 2 ion combining with the nitride ion, so it's chromium 2 nitride. Okay, so in naming this compound, you have to do all this work to figure out what is the Roman numeral that's going to be accompanying chromium. Okay, naming ionic compounds, if a polyatomic is involved, is the same way. You just take the name from the polyatomic table and drop the word ion. So ClO2 here in the polyatomic table is the chlorite ion. This is the potassium ion. Together it's just potassium chlorite, and I drop those names ion. Okay. Keep in mind though, if the cation is one of these things that requires a charge, I have to figure out that charge and identify it with the Roman numeral. Let's do some practice problems. Feel free to pause the video here and try this yourself first before continuing to watch me solve this problem. We'll start with KCl. This I can look at the periodic table and recognize K is not a transition metal. It's always +1. I don't have to worry about Roman numerals. Chlorine is -1. The positive ion here, potassium, is just called the potassium ion. The Cl is called the chloride ion, right? Chlorine becomes chloride. And when naming this, I drop these words ions. So it just becomes potassium chloride for KCl. Done. Second, BaOH2. Barium, alkali earth metal, it's just always 2+, the barium ion. So I just have barium, I drop the ion. OH I recognize from my polyatomic table as hydroxide ion. I drop the word ion, and it just becomes barium hydroxide. I don't have to get Roman numerals involved here because the cations are always the same charge. Potassium is always +1, barium is always +2. If the cation is a transition metal, it probably has different charges, like iron. Remember, there are 3 exceptions to this transition metal rule. Silver, cadmium, and zinc generally don't have Roman numerals because they're generally always the same charge. Just like barium is always 2+, zinc is always 2+. So I don't have to call it zinc 2, it's always 2. Iron, though, can have a bunch of different charge states, 1+, 2+, 3+. So here, let's first determine what charge it has before we name it. We know just by looking at it, it's going to be called iron something, right? There's some Roman numeral that's going to go in here. And it's combining with chlorine, which becomes chloride. So I already know the name is going to look something like this. But what is the Roman numeral? Again, I use this sort of matrix to figure out what the charge is on the iron that I'm going to write up here, and the Roman numeral then that I'm going to write in here. I start by identifying what is the charge on chlorine. It is a halogen, it is always -1. There's 3 of them, so I multiply going down here, and it's 3-. This 3- is always balanced by 3+, because overall the compound has to be neutral. And now going up, I divide 3+ by 1. There's 1 iron, so it's still 3+. And so the charge on iron is 3+, and the Roman numeral is then 3. The name of this compound is iron 3 chloride. That's all for ionic compounds, right? Remember, ionic compounds we discussed in the previous video are always metals with nonmetals. Molecular compounds, right, we classify differently. They're molecular because they only have nonmetals. Things like sulfur, phosphorus, nitrogen, carbon, oxygen, hydrogen, fluorine, chlorine, etc. Those elements, those nonmetals on the right side of the periodic table, right, when they group together, they're molecular compounds. And they have a different naming convention, right, than ionic. Ionic always had this sort of cadence to it, an element, right, and then an ion. Maybe that ion's ending in IDE unless it's one of these polyatomics. Here, though, we're going to get prefixes involved as well. Okay, so in addition to suffixes, sulfur is still going to be sulfide, fluorine is still going to be fluoride. Okay, but the thing that comes first does not have a suffix, just like it didn't before in ionic. Okay, the difference here is that we have to name this compound based on the numbers of each element. We didn't really do that necessarily with ionic compounds, but molecular you do. And those numbers we're going to label with these Greek prefixes. And you know some of these already. 3 is tri, like triangle or tricycle. Right? 5, pentagon, 5 sides, penta. Right? Octa, 8. So some of these you're already familiar with, but do memorize all of them. Okay? So that we can name these accordingly. So for P, I'm just going to call it phosphorus. That element comes first, so I'm just going to write the name of that element. Before it, I'm going to write the number with the Greek prefix. 4 is tetra, so I call this tetraphosphorus. Sulfur, this element is coming second, so I'm going to change that suffix to sulfide. And there's 3 of them, so it's trisulfide. So tetraphosphorus trisulfide is what I named this. For similar reasons, I can name this second one. Xe is just xenon. Fluorine becomes fluoride. There's 6 fluorines, so it's hexa. Okay. One interesting point here is the xenon is a 1. So you might be tempted to call this monoxenon. Okay, but this is sort of the exception to this rule. If the first element is just 1, I don't use mono. I will only use mono if it's applied to the second element, not the first element. Again, we don't add a suffix to the first element. We don't add mono to the first element. We do add all these other ones to the first element. For the second element, we use all of these, and we change the suffix to IDE. Sometimes you'll see some of these combinations written 2 different ways. Here is dinitrogen, 2 nitrogens, pentaoxygen, so pentaoxide. Sometimes you'll see these 2 vowels in a row grouped together and just made into here an O, so the A is dropped, just so it's easier to sort of say pentoxide. So this would be dinitrogen pentoxide. Sometimes we shorten that prefix by a vowel for the elements that begin with vowels. So let's practice a few more of these. Feel free to pause the video here and try it yourself first. Again, these are molecular compounds, right? Here it's specifying, but even if I didn't write this and you have to name these, okay, you're going to know to use the Greek prefixes here because these are both nitrogen and sulfur nonmetals. So it must be molecular. I must need these prefixes. I don't use these prefixes in ionic compounds, but I do for molecular. So here for the first one, N is nitrogen, S is sulfur, but that becomes sulfide. And then I apply the prefixes. If it was just 1 nitrogen, I wouldn't add mono. But if it's 2 through 10, I add the prefix. Here it's a 4, so that is tetra. The prefix for 10 is deca, so this compound is tetranitrogen decasulfide. Right? 4 is tetra, 10 is deca. P2O4, P is phosphorus, O is oxygen, which becomes oxide. 2 is di, Di. 5 is penta, but sometimes we shorten that and drop the A to just pent. So the second one here should be diphosphorus pentoxide. Okay, so that was naming molecular. Before that, we were naming ionic. Now let's name this last class, acids, right? And acids, you'll remember, always have this telltale H in front. Okay, they can be either binary, 2 elements, in which case we have 1 naming convention, or they can be ternary, in which case we have another naming convention. So binary means 2, so if it's just H and 1 other element, then we use hydro and an ic acid at the end. Okay, so chlorine becomes hydro, chloric acid. Chlorine becomes hydro, chloric acid. Okay, so what would HBr be? It would be hydro. I know there's going to be an ic acid out here at the end. And for bromine, it's bromic. You drop the suffix ine, okay, or IDE. And these chlorides, fluorides, or chlorines and fluorines, right? Iodine becomes iodic. For ternary acids, it's a bit more complicated. You have to sort of remember one extra rule. Okay, so ternary acids, remember, are an H combined with a group of atoms, one of which is going to be oxygen. Okay, so sometimes they're called ternary oxyacids. So ternary means 3 elements are involved. So let's look at maybe HNO3. So this is hydrogen combined with nitrate ion. Now, the naming convention here is not hydronitroic acid or something, right? We're only using the hydro and the ic acid, okay, for binary. For ternary, it goes like this. You don't use hydro. You identify the polyatomic. If it's 8, you change it to ic acid, okay? So the way I'd like to remember this is if you ate too much, you feel like ic, right? So if it ends in 8, you add ic. So this nitrate becomes nitric acid. We don't add the hydro for ternary compounds like this. So this is nitric acid. So contrast that with NO2. So for HNO2, I identify this as an acid. Certainly looks like it. It begins with H. I then remember NO2 or go to my polyatomic table and see that NO2 is nitrite. Ite, we change to us. So you eat too much, you ate too much, you feel icky. Okay, if it's ite, it's us. So this becomes nit. We change the ite to ous. This is nitrous acid. Okay, so that's naming acids, molecular compounds, and ionic compounds. Okay, this is really pivotal as we move forward and start to come up with chemical reactions, right? Based on just describing things reacting together, right? Hydrochloric acid plus sodium hydroxide, right? A balanced neutralization reaction. That's what we're moving toward. But first, we really have to master this language of chemistry to get there. That'll do it for this video. As always, feel free to like and subscribe to my channel on YouTube. Check me out every week over on Twitch, where I do office hours, answering whatever chemistry questions you might have. Or check out my previous video to this lecture if you need more help, or my subsequent videos as we build up to balancing chemical reactions and stoichiometry. That'll do it for this lecture. See you next time.